Hello, I'm Muhan Lin from Chinese University of Hong Kong, Shenzhen. This summer, I worked with Shibo Zhao and Professor Sebastian Schara on a robust visual inertial odometry with active visual extraction. The visual inertial odometry is an effective method of estimating poses, which integrates the feature checking on camera images and the inertial measurement units motion information. However, in visual degraded environments like this, dark and long corridor, the VIO has a poor performance. The number of flawed or less informative features in such environments increase, that will decrease the accuracy. Additionally, sometimes we have to use micro vehicles like this small drone. With limited resources, we cannot conquer the problem of large time consumption caused by the large number of feature points. These are some of the reasons why VIO has poor robustness in such environments. Therefore, we desire to select the feature actively to filter out such flawed or less informative features. This is the overview of the new system proposed by this work. We developed the system based on the thermal point TIO system as the baseline, and our main contribution is this stage, the active feature selection. After each image arrives, the system first performs RMU pre-integration. If it is not the first image, the system will conduct photometric checking followed by active feature selection. After this, the system will extract features with thermal points and enter these newly extracted features into the next iteration of image processing. At the same time, the results of active feature selection will enter the backend and participate in the stages of triangulation, PNP, and local boundary adjustment. We adopt the thermal point method to extract feature points. From this picture, we can see that the thermal point method gets influenced by the photometric changes list. Therefore, it can extract more stable features than other methods. Then we select the feature actively with the feature uncertainty quantification, maximum singular value powered by -1/2. The maximum singular value is obtained from the SVD decomposition of the intensity gradient covariance matrices. The basic idea is to utilize this intensity gradients with respect to the x and y direction and format this M matrix as covariance matrix of intensity gradients. Now we get the singular values with SVD decomposition. Among the singular values, the maximum one should represent the largest intensity differences between the current point and the pixels around it. This ellipse, centered at the analyzed point, visualizes the intensity changes around this point P. We consider all the points on the edge of this ellipse have the same intensity. Therefore, the distance between the point P and any point on the edge should represent the path length the point P needs to move to change its intensity at this point to the intensity on the edge. Therefore, the short half distance should be the shortest path length for delta I edge minus IP. Because the maximum lambda quantifies the largest intensity differences, therefore, this path its size should be quantified by the maximum lambda powered by -1/2. And the direction of this axis is the direction in which the intensity changes fastest. Similarly, the long half distance should have the size quantified by the minimum lambda powered by -1/2, and its direction is the direction of changing slowest. What is need to pay attention to is that we select a feature actively with uncertainty quantification based on the maximum lambda, but not the minimum lambda. The reason can be seen from this picture, from this feature point. We can see that the intensity gradient in the x-axis is very large, and the direction of the x-axis should be the direction in which the intensity changes fastest. According to this visualization, the uncertainty in the direction of changing fastest should be quantified by the maximum lambda upon by -1 or 2. Therefore, the x-axis should correspond to this uncertainty quantification. And on the other hand, the intensity gradient of the y-axis is very small. It's always 0. And the direction of y-axis should be the direction of change slowest. According to the visualization before, the uncertainty of this direction should be represented by this, the minimum lambda upon by -1 or 2. Therefore, if we select features with this value, we will get a conclusion that this point is not a feature point. However, if we select features with this quantification, the maximum lambda upon by -1 or 2, we can tell that this feature is an informative feature. And it is consistent with the ground truth that this point is an edge point. There come the results of our algorithm. We tested the algorithm of MMPUG datasets, which were extracted in such a long and dark corridor. We successfully decreased the residuals to 56.23% of the residuals from the original TBTIO without increasing processing time and CPU rate of checking. This video is the real-time output. It's the real-time output of our algorithm. The points marked with circles are those accepted points. The circle's radius is computed with the maximum lambda upon by -1 or 2. So the radius of the circle should represent the uncertainty of the features. We can see that the features of the edges have very small radius, and the features of the corner also have very small points. The features on other places like the walls and the floors, they have relatively large radius. Therefore, the output of our algorithm is consistent with the ground truth. The selection of our algorithm makes sense. And this is the estimated trajectory obtained by our algorithm. The ground truth route is to start from one point and goes for a very long distance to the other point, and then goes back in exactly the same trajectory and back to the starting point. So the ending point and the starting point should be the same. We can see that the estimated trajectory shown here, the routes from the starting point to this point, the route from and to this point are very close to each other. The drift is very small. I will show a comparison of the estimated points generated by this improved algorithm and the original algorithm. We also switched the threshold of the maximum eigenvalue upon by -1 or 2, the feature filter, and analyzed the algorithms in terms of the trajectory residuals, the checking time, the CPU usage, and the number of filtered points. We can see from these pictures that the checking time and the CPU usage do not change a lot because of our the feature selection, but with the optimal max eigenvalue threshold, which should be 750. According to this graph, the residual can be reduced to almost half of the original point. The infimum threshold represents the algorithm without feature selection, and the residual here is almost half of the residual of the original algorithm. These are the comparison of the trajectory of the original algorithm and the trajectory obtained by our improved algorithm. We can see the large drift between the route from this point, from and to this point, which should be exactly the same corridor. There's a big drift between these two routes. The drift has been reduced to a large degree in this picture, and there are many noisy point clouds near this trajectory obtained by the original algorithm, and these noisy points have been cleared to a large extent as well. So there comes the conclusion. We developed an information-driven value and proposes a criterion with an evaluated threshold obtained by the experiments for effective selection of informative features. We conducted the experiment evaluation in challenging environments and successfully increased accuracy and robustness. However, the performance currently depends on the fixed threshold obtained from experiments. In the future, if we can develop the adaptive threshold based on the current feature number, we can make the algorithm adapt to the environment in a better way. These are the references, and thank you for your listening.